Moving on to level 5.2, which we're going to cover one-to-one functions and inverse functions. So the first thing, determine whether a function is one-to-one. So one-to-one is just like playing man defense, if you want to think about it that way. For every person on your team, you're covering one person on the next team. And functions can be described that same way. So we say, by definition, a function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. So that is, if x1 and x2 are two different inputs, then they go to two different outputs. So we don't have, say, if I plug in 2, I get 4. And if I plug in -2, I also get 4. Those are not, the one that I just described is not one-to-one. So every x gets exactly 1 y. That's usually what we mean when we describe something being one-to-one. Now, if you see this picture, we have our domain as modeled as x and our range modeled as y, and every x goes to a unique y value. If not, then we don't call that one-to-one. It still is a function if every x goes to all y, but if it goes to exactly one y, then we call that one-to-one. And it's very powerful when we have one-to-one functions. So let's just look at these first two examples. Determine whether the functions are one-to-one. So I see that Indiana goes to Washington goes to a unique number. South Dakota goes to a unique number. North Carolina goes to a unique, and Tennessee goes to unique. So we would call this a one-to-one function. Now there is a fancy name for this mathematically. The fancy name for one-to-one is called injective. The opposite is if every x goes to a y, we call that surjective. And if we get both of those together, we call that a bijective function. But that's more than you need to know. If you know the words one-to-one, then I'll be super happy. For b, we're checking that every x goes to a unique y, so -2, 6, -1, 3, 0, 2, 1, 5, 2, 8. All of those are unique, so this would be described as one-to-one because every x goes to exactly 1 y. So if we want a full definition, that's what we get. Another way to tell if a function is one-to-one is if you know what the graph looks like, you can use something called the horizontal line test. Now we've used a line test before. We used the vertical line test to see if it's a function or not. The horizontal line test tells if a function is one-to-one. So what the horizontal line test says, if every horizontal line intersects the graph of the function in at most one point, then f is one-to-one. I should say then. So we know these two functions. We've seen them 100,000 times. If we graphed y equals x squared, or f of x equals x squared, that is our friend, the parabola. And then we have g of x being x cubed. That is our friend, the chair function. Looks something like this. Again, we've graphed these 100,000 times. Looking at x squared using the horizontal line test. Drawing in one horizontal line, we see that if I plug in two different x values, I get the same y value out. So x squared is not 1-to-1. X cubed, on the other hand, is. Because if we drew in a horizontal line here, or here, or here, or here, you see that our graph is hit only once. Only once. Since that's the case, x cubed is one-to-one. So for every x, we get a unique y value back out. And this is quite the pattern for even functions or odd functions. Odd functions are one-to-one. Even functions are not. All right, let's flip it over. So why I spend a little time talking about one-to-oneness is because it gives us inverse functions. So definition of an inverse function. Suppose f is 1-to-1. then for each x in the domain, there's exactly one y in the range. So the correspondence from the range of f back to the domain of f is called the inverse function. In other words, to find the inverse of f of x, we just switch every x with its corresponding y. And really what it does is if we have a map, let's say this is our domain, this is our range. We plug in a number in our domain, it maps to our range. If we wanted to get back to the original, we need something that undoes what we just did. So our range then becomes our domain, and our domain of our original function becomes our range. We're just switching our x's and our y's. So let's start off something easy. Find the domain of the inverse function for the given graph. So our original are the states. Our range for our original is the population. So the domain for the inverse, and the way we write inverse is to the negative first power. So you'll see here, we read this as f inverse, f inverse, f inverse. Then this would be our outputs from our original. So we'd write that as 6.2, 6.1, 0.8, 8.3, and 5.8. This is our domain for our inverse. And I know it didn't ask, but let's write it. What's the range of our inverse? So our range of our inverse is Indiana, Washington, South Dakota, North Carolina, and Tennessee. I just used the state abbreviations. All right. So knowing that inverses are switching the x's with the y's if our function is one-to-one. It says find the inverse of the following one-to-one function. Okay, so we know that it has an inverse, and we're just going to switch the x's with the y's. So here, find the inverse. It's going to be our set. The first, instead of negative 3, 27, we're going to have 27, negative 3. Instead of negative 2, negative 8, we're going to have negative 8, negative 2. Same thing, negative 1, negative 1. We switch our x's and our y's. 0, 0, that's easy. 1, 1, it's easy. 2, 8 becomes 8, 2. And 3, 27 becomes 27, 3. So with sets of numbers to find its inverse, we just switch the x's with the y's. Now, the inverse function, as I just described, so this is formalizing it, is written as f inverse, not f to the negative first. And this undoes the original function. So we kind of already did this in 5.1, we just weren't saying it. If I plug in the function to its inverse function, they undo each other and we're left with x. Likewise, if I plug the inverse function into our original, I'll get x back out. This is the composition of two functions. So just for an example, because this looks like a lot of gibberish, let's say we have our two functions, x squared, and we know what undoes x squared. We know that that's square root of x. So if I plug the square root of x in, if I find f of g of x, then that is the square root of x squared, which is just x. Likewise, g of f of x, if we have the square root of x squared, we also left with just, well, this is a special case, but we're left with x. Now, I will say this is a special case because this is really the absolute value, but we don't want to worry about that. So this is a nice little example. Let's flip it over and work on some inverses. So with example 5, we want to verify that the inverse of g is cube root of x. So the way we verify that is, just like on the previous page, we want to show that g of g inverse of x equals x, and g inverse of g of x equals x. So just like we did with composition of functions, I want to plug in the cube root of x into g. So that's the cube root of x cubed, which is just x, which is what we want. Same thing, the inverse of x cubed. So plugging x cubed into the inverse function, we get x cubed root. And if we remember our properties of exponents, cube root is to the 1/3 power. So this is x to the 3 over 3, which is just x to the first, which is what we want. So this verifies that the cube root of x is the inverse or the undoing function of x cubed. Likewise, verify that these two are inverses of each other. So I want to show that f of f inverse of x equals x and f inverse of f of x equals x. Now, we also want to say that if we're plugging f inverse in, provided that x is not equal to 0. Because if x is equal to 0, then f inverse doesn't work. Likewise, if we're finding this, we want to say provided that x is not equal to 1. Because if x was equal to 1, then plugging f into this function doesn't work. So, our inverse function, we want f of 1 over x plus 1. So then plugging this in, we get 1 over x plus 1 minus 1. Those cancel. I have 1 over x, which is just x. So that works. How about f inverse of f of x? Well, this is f inverse of 1 over x minus 1. So this is 1 over x minus 1 plus 1. So flip the guy, x minus 1 plus 1, which is just x. So that works. So this is what we do when we're trying to verify something is an inverse function. Now, graphically, because we always go back to the graphs, the graph of a function and its inverse are symmetric about the line y equals x. Now, why is this WHY? Because, like we said before, inverses switch the x and y values. And when you do that, so a2, b2 becomes b2, a2, these reflect over the line y equals x. They reflect over this line. So if you know how to graph the function itself, and you know how to graph the inverse function just by reflecting it over the line y equals x, then that also gives you some insight to both the domain and the range of the function and its inverse. All right, next up. So how do we find the inverse of a function? Well, there's 3 steps that we want to do. So step number 1, in y equals f of x, we're going to interchange the variables x and y to get x equals f of y. So we're going to switch the x and y terms. Second step, we're going to solve for y in terms of x. And then third step, we're going to check that our function really is the inverse. So let's try this out. Find the inverse of 2x plus 3. So step 1, we're going to write it in terms of y. So that's kind of step 0, because it didn't really include that. So really step 1, switch the x's with the y's. So this is x equals 2y plus 3. So wherever we saw an x, we wrote a y. Wherever we saw a y, we wrote an x. Next, we're going to solve for y. So we're going to subtract 3. So x minus 3 equals 2y. And then we're going to divide everything by 2. So I get y equals x minus 3 over 2. This is our inverse function. And then for our check, what we want to show is that if we plug this into our original, that f of f inverse equals x. So if we just show this, then we get 2 times x minus 3 over 2 plus 3. These 2's cancel, x minus 3 plus 3. Those cancel, we're left with just x. Likewise, if we check that f inverse of f of x, we'd also get x. I know you can do this on your own, so I'm going to leave that up to you. Once we get into the more interesting cases, so when we have x's maybe in a rational function, then we have to do a little bit more work. So step 1, instead of writing f of x, let's write y. Y equals 2x plus 1 over x minus 1. So step 1, switch the x's and the y's. So wherever you see a y, we're going to write x. Wherever you see a x, we're going to write y. So that's step 1. Step 2, solve for y. So first things first, we're going to have to cross multiply. So we have x to y minus 1 equals 2y plus 1. Then we're going to have to distribute. So I have xy minus 1x equals 2y plus 1. Here, this is what I'll really know. Get y's on same side. So in order to do that, I can either subtract 2y or subtract x. I'm going to subtract 2y. So I'm going to subtract 2y here. I'm also going to add x at the same time. So I have xy minus 2y equals x plus 1. Now, what's common between these two? So I'm going to factor out a y. So y comes out. We're left with x minus 2 equals x plus 1. Last thing, divide by x minus 2. So y equals x plus 1 over x minus 2. And this is our inverse function. So let's try one more of these. Find the inverse as long as x is greater than or equal to 0. So step 1, write it in terms of y. Let's do this in a different color. So we have y equals x squared. So we have x equals y squared. Now, to solve for y, we take the square root of both sides. And remember, when we take the square root of a variable, it's really saying square root of x equals the absolute value of y. And this is what I was trying to say earlier. Because the square root, both of these have to be positive. So really what's implied is the absolute value. That's what we get plus or minus square root of x equals y. And we're saying x is only positive. So there's no way that we are ever going to have a negative in here. So that way we'll never get a negative out. So then our simple inverse function is the square root of x. This is our condition that we put on our domain. All right, so that takes care of inverse functions and one-to-oneness.